Thanks so much, Amber, for that kind introduction. And thanks, Daniel, for being here as well. We've got a very neat kind of co-seminar today, co-webinar today, talking a bit about mathematical modeling and some of the foundations of that mathematical modeling, as well as the real application here. And that, I think, really puts a nice embellishment on these seminars because we talk a lot about physics, and I'll speak about that today. We talk a lot about software modeling approaches, but it really is all in vain unless we have someone that can do something with it, right? And that's why I'm so glad Daniel's here with ABEC because they're doing things, using the code to create actionable insights that I think is very intelligent, a nice capstone to what I've been talking about for a year and a half now in these webinars. And so I'm very grateful that Daniel's here. Like I said, ABEC, they are I think some of our smartest users in terms of how they can use this tool to improve equipment, process, etc. So I'm thrilled that we have this opportunity to collaborate. So we're going to talk about, well, as expected, single-use performance, single-use bioreactor design and performance comparisons. I'll begin by speaking a bit about some of the modeling theory and principles behind the scenes in the context of MSTAR. We'll then turn it over to Daniel, who's going to talk about applications again within the context of their systems and how they use MSTAR within a real manufacturing environment to make better bioreactors. I'll introduce MSTAR first, and then I'll give a brief, maybe 15, 20-minute introduction. Then I'll pass the baton over to Daniel. MSTAR, as we've spoken about before, is a software company, and our goal is to generate big models that are digital twins that allow us to generate predictions and develop first principles models for scientists and engineers. So people that use MSTAR typically are, engineers, scientists, research scientists, etc. Our goal is to make predictions that are indistinguishable from measured data. Okay, that's a tall order, but that's our guide. We want the time evolution of the salt concentration at a probe predicted from the model to match what would be observed inside the simulation. We want the fluctuating forces on an impeller blade to match what you see inside of an experiment. We want the time evolution of the KLA and bubble size distribution to match what you'd see inside of an experiment. So the goal here isn't just to get conceptual oversights or some sort of roadmap of how a system behaves, but actually be able to predict from bubbles all the way through PID controllers how that system is going to behave and how those systems mechanistically interact in a way that mirrors what we'd see inside a manufacturing environment. Key differentiators, MSTAR was born and bred to run in GPUs. I talk about this every time, and I'll talk about it again today because it is such a big deal. It is such a big deal. And if you're not embracing this hardware, you're getting behind, and I'll emphasize that point in a minute. This embracement of GPUs allows us to run orders of magnitude faster than conventional modeling products. I'll speak to that again as I go through this presentation because this is a point that must be made. Okay, this isn't a Burger King versus McDonald's comparison. This isn't a Nike versus Adidas. This is Delta Airlines versus a wheelbarrow in terms of getting people and data and information across large spaces. And this allows us to investigate problems that are previously impractical, as we'll speak to today. Timeline, for those who might not be familiar, we started operations in 2015, and then we have just joined Siemens. And like I said, we're thrilled by that and the opportunities it presents. So again, MSTAR is a platform for building physics-based digital twins. What I mean by that is we're solving governing equations of transport, things like the Navier-Stokes equations for predicting fluid flow, things like the advection diffusion equation for predicting species transport, things like Newton's second law for predicting particle-particle collisions. We're not appealing immediately to correlations, as it were. We're solving conservation laws. And this allows us to model systems at the level of the transport carrier. By transport carrier and fluid mechanical systems, I mean things like the individual eddies, okay? And here we have some mixing tank that's agitating this semi-batch system where we have fluid being added, and it's agitating across it. Here we have a manufacturing facility where there is a leak of gas. That gas and the constant increase in concentration will trigger a purge of the room. So we have time-accurate fluid mechanics simulations, we have concentration dispersion, as well as inline controllers, okay? And that's kind of the neat bridge here. So we can go from bubbles and eddies and LES simulation all the way to facilities design within one simulation. We don't have to use intermediate, lookup tables or whatnot. We can see how, the fluid viscosity and its influence on eddy structure ultimately informs how we might tune the gain on a PID parameter, which is pretty cool to have that holistic understanding of how these systems behave. We primarily focus on chemicals and biopharma. So again, MSTAR's general purpose, and we're solving general purpose fluid mechanics and particle mechanics equations, but the way it's bent is primarily towards unit operations. Continuous flow, of course, but we're looking at, again, how processes can evolve over space and time, whether that's in chemical engineering, whether that's, particle CFD DEM simulations, whether it's classic mixing simulations with reactions and chemically reactive turbulent flows, or bioreactors, which we're talking about today, where we have mass transfer between the bubbles and the aqueous phase. We have mixing, we have pH changes, we have biomass growing, etc. But again, MSTAR is general, but we have tailored this tool to be designed for the process engineer, okay, which is a very relevant space to operate in for a tool like this. As I mentioned, MSTAR was designed from the ground up for GPUs, okay? And this was a purposeful business decision. In fact, in 2025, MSTAR does not even run on CPUs because there's no point to, all right? The divergence in speed between what you can get on a GPU versus what you can get from even a leading like Granite Rapids CPU is so substantial that it's not worth even discussing how many CPUs it would take. Oh, it's worth discussing. It would take hundreds or thousands of CPUs to reproduce the power of one GPU at this point. Listen, I love CPUs. I'm using a CPU now. CPUs are great for running operating systems. CPU can handle very complex operations, but they're not compute dense. You get 4, 8, 16 cores. Maybe you got a monster that's 96 cores. And so they're great for these serial complex operations, but they're not great for dense math. A GPU is different. A GPU has tens of thousands of cores, okay? They're not as complex as a CPU core, but they make up for that lack of complexity in sheer number, okay? And so they're perfectly parallelized they're perfectly suited for massively parallelized algorithms, which is what we've always written. We've always written codes that are designed to run across 20,000 cores. And so these things have gone hand in glove. And so foundationally, and I'll speak to this momentarily, we can run simulations orders of magnitude faster. Not percent, orders of magnitude, as I'll speak to here on the next slide. And yeah, a lot of old codes, you can try to retrofit them to fit on a GPU and offload some of that physics and math, but foundationally, you're not going to get that full gain. It's like I can put a spoiler on my Civic, and yeah, it's going to help, I guess, keep the rear tires engaged, but like it's not doing really all the spoiler can do, and my Kia is never going to take advantage of all those kind of advanced, I should say, modifications. I don't have a Kia. I don't have a spoiler on my Civic, but it either way. So MSTAR captures this change in speed, and it's not just saying it or arguing it or claiming it. It's in the literature. Okay, people are reporting on this. All right. So here was a paper just earlier this year by Unilever and University of Manchester. MSTAR wasn't involved in this paper. This is just third-party research, but it's academic research published in the Journal of Chemical Engineering Science. And this is a study on mixing of two miscible fluids in turbident stirred vessels, as it were. And here's the punchline. The MSTAR method, leveraging GPUs, took approximately 4 hours with the simulation. Star CCM took about 41 days. Okay. And now we're part of Star CCM, so I love Star CCM. But just to be, I'm going to toe the company line, of course. But to be sure, like that's a step change in performance. And if you read the paper, the predictions for MSTAR are better. All right. It's not just, I don't just rag on Star CCM. I love that product, of course, but ANSYS as well. Here was an article a couple years ago looking at cell growth kinetics and how intracellular reactions evolve over time. It seems to be structured kinetic models. MSTAR is running about 85 seconds per second. That just takes 85 seconds of hold time on a pretty modest desktop GPU to run about 1 second of actual cell growth. Using ANSYS, it was somewhere around 100,000 seconds per second. So I'm not just saying this. I'm not just claiming this. And we're not just doing speed for speed's sake. When you can run this much faster than kind of the state of the art, it changes how you use simulation. Even as these tools begin to port to GPUs, like good news, we're 2 times faster. We're 3 times faster. You should be hundreds of times faster when you're on this hardware, given the amount of math it can do. And that hundreds of times faster is where we're at, as it were, because we're born and bred from the ground up to exploit it. This acceleration allows us to bridge the impossible timescales, okay? Now, these are pretty simple simulations, but I'll speak to them. And what's interesting is these both ran like over lunch, okay? So here we have a dissolution tank. We have a CFD DEM simulation where we're trying to get particles off the bottom of the tank. And this is multi-phase. We've got a free surface here and a vortex forming, and obviously multi-phase with the solid liquid the solid particles down here. In tandem with all this time-accurate CFD DEM simulation, we have system control. We have a PID controller wired up. We're dynamically tuning the impeller speed in order to achieve a target suspension ratio. Like that's the idea of bridging what people wouldn't have done before. Like transient fluid mechanics with DEM that's kind of a big deal. But then to couple that with process control and to run it while eating a sandwich, like that's what's bridging. That's what's possible now with these types of algorithms. Here again is more of a multi-phase system involving gas and liquid. Here we've got gas bubbles sparging in, being broken up by the action of the impeller, coalescent, of course. But we're tracking every individual particle, every individual bubble, as I say, as it undergoes these breakable coalescence events. So as we attack physics at the level of the individual transport carrier, in this case, tracking every bubble collision, tracking every bubble breakup event, it allows us to actually make simpler models because foundationally, the physics that govern bubble breakup and coalescence at the level of the individual bubble and individual bubble pair is simpler than sometimes these alphabet soup population bounce models that must be used when you can't do this, okay? So again, the more physics you can capture explicitly, believe it or not, the simpler the model becomes. And you can believe that because it's actually it should be kind of self-obvious. What's neat about this as well is this isn't just a specialist tool. So here I'm showing kind of a few papers that we've written over the past few years. And the slide serves two purposes. One, MSTAR is very well validated, okay? It's being used by a lot of different organizations in a lot of different areas to solve some very hard problems, and it's working very well in those spaces. This is 6 of dozens that we published in the last few years, or others have published independently. Second, we have both CFD experts and CFD newbies using MSTAR to create publishable data, okay? These 3 papers here, written by people that have been using CFD for decades, okay? Very smart users. These papers here, I kind of led the authorship on this guy, but these guys are written by people who are not CFD experts until they started using MSTAR. And they're able to develop data and build models that made publishable quality results in months or a year, okay? And that's kind of the inflection point this presents. It's not just a tool for people that already have their head in CFD. It's a tool that allows biologists, okay, to start running CFD to optimize their processes, okay? And that's cool because it expands who we can speak to. And again, the things we're talking about today are particularly related to some of this momentum in species transport. And I want to emphasize, again, when we're attacking these problems, we're solving them at the level of the transport carriers, or we should say at the level of the conservation law. When we're solving and predicting fluid flow, we're not looking at some mean correlation. We're solving the Navier-Stokes equations using an LES closure model at each of these voxel points, and are able then to predict the time evolution of the fluid flow in response to potentially time-varying operating conditions, changes in impeller speed, etc. We're solving the time-dependent advection diffusion reaction equation to predict how species move in tandem with this fluid flow. And this can all be coupled. If this thing is changing the viscosity of that fluid, no problem. If this thing is reacting and as it makes different species, no problem. Because we're solving these physics in tandem and appealing to the same transient conservation laws, it becomes very easy to layer on degrees of complexity in multi-phase and multi-physics problems. Okay, as I mentioned earlier, bubble dynamics, believe it or not, and this should be obvious, we can talk about this later, we published about this a lot, becomes easier to model when you can capture them explicitly, okay? For those who know that a population balance model is going to be a work of art, and it'll be a precision-tuned work of art, okay? That is, I hope you don't nudge it much because those parameters are often tailored to a specific set of operating conditions and a vessel topology. And because those models aren't capturing bubbles explicitly, they're instead using some sort of statistical representation of the bubbles across some bin diameter space. When you can just track the stinking bubbles, we can just track all 10, 100 million of them, your models become simple because bubble breakup mechanics are volume agnostic, okay? The way a bubble breaks up doesn't care how big the vessel is. The way 2 bubbles coalesce is independent of how big the vessel is. So if you can describe your bubble transport physics and your multi-phase transport phenomena in terms of these individual bubble transport relationships, there's breakable coalescence, you have one relationship to rule them all. You can use the same correlation in lab scale, pilot, and production because you're modeling the system at the level of these carriers, as it were, which is what is enabled by these more sophisticated hardware architectures. I have a couple more slides, and I'll turn it over to Daniel to talk about why this matters in practice. But again, you need to understand is that we can go far beyond just looking at colored heat maps on a CFD simulation and looking, ooh, the velocity is red near the impeller. Ooh, it's blue near the top of the vessel. We can go way beyond that and actually model the stinking process. And again, I spoke about these PID parameters. We can put in DO probes into the simulation, put in a delta V or any sort, I should say a Siemens controller, and see how like deviations between the set point and the actual process variable inform a controller logic, which forms a process output, or rather just, I should say, control variable. In this case, difference between the DO set point and the DO probe reading inform the gas sparge rate, or how difference between the target glucose and the realized glucose, as bugs and cells are eating up the nutrients, and the target glucose are informing the feed rate of the feed into the media. And that's kind of the point here, is we can start to simulate entire processes. Okay, and I showed this movie before, but I showed us actually simulating. Here we're actually looking at how different step changes in operating conditions inform system response. So this is published with Bristol Myers Squibb, but they had some sort of delta V PID controller system governing the performance of the reactor. They have a given set speed and DO set point. They then increase the set speed. The system responds, of course. Initially, the dissolved oxygen level goes up because we're making more utility out of that gas coming into the vessel. And the PID controller gradually walks back the sparge rate until the realized DO concentration, shown here in black, matches the target value, which is 40%, as it were, shown in the red. We then increase the DO set point from 40 to 60. And again, after about 20 minutes or so, the system responds and recovers the steady state value by increasing the flow rate in the presence of this higher impeller speed to realize the new operating conditions. We step down, drop the impeller speed again. And again, after about 20 minutes or so, the action of the PID controller increases the gas flow rate in a way that allows the KLA to go back to its necessary value in order to achieve the target DO set point. So this black line shows this response of the system over time to these step changes in operating conditions. The blue line, M-star, okay? We're not telling the M-star anything about this controller response. We're not giving it the answer ahead of time. We're giving M-star the physics, the fluid mechanics, the fluid properties, and the controller parameters. And then once we have that, we can reproduce how the systems can behave in time in response to changes in operating conditions, not only at the level of the physics, but at the level of the actual controllers. And this answers the question, what should my gain be? What should my integral reset time be? It allows us to tune those parameters in a way that optimizes the performance completely in silico. And more importantly, understanding why it should be that way, why we should use this gain, why we should use this reset, why all the way back to the level of the eddies coming off the impeller why, and all the story between the two. We can incorporate reactions into this thing. Look at how pH evolves over time in response to, say, CO2 sparging or CO2 stripping. Again, whether they're buffer reactions or cell growth reactions, this is all in play. And that is, we have this holistic understanding of how the system behaves over time, because we understand it from transport carriers to actually process dynamics. And again, whether it's fast reactions like this, or whether it's slower reactions like cell growth or whatnot, it's in play because the reaction's a reaction, quite frankly. So again, those are some of the highlights I wanted to make when introducing the software. We've moved way beyond, okay, the steady state RAN, CFD, and correlation-based modeling. Yes, they're great. I love correlation. I use them every day. But foundationally, what we're able to do now are build these true digital twins that allow us to go, from soup to nuts, as it were, from transport carrier to actually process behavior and control and all the bridges in between, and understand the physics driving process outcomes. The step change guys have motivated GPUs, okay? And GPUs don't just introduce a 4x speed up, as it were. They're like, oh, now we're running twice as fast. They present orders of magnitude more compute capacity. Okay, you should have hundreds of times, a factor of 100x if you're going from a small CPU cluster to a small GPU cluster. And these models are becoming increasingly indistinguishable from measured data. That's our objective. That's our objective, as it were, to put two data on the screen and be able to show and not be able to identify which one came from the model, which one came from the simulation. Okay, so this is where MSTAR is coming from, all right? And kind of our perspective building these models. It's great. I love it, but it means nothing if we can't do anything with it, okay? The models are compelling, but if I can't get them off my laptop, then they serve no function. And so the real sizzle here is how people can actually take these data and turn them into actionable insights and make real things, as it were. So Daniel, that's where I think your company comes in and can actually make these actionable in a way that doesn't just make pretty movies, but makes this field a bit more useful and efficient. Daniel, I'll let you take it away with yours. You're on mute, just FYI.
All right, thank you, John. So just really quick, many of you may already be familiar with what ABEC does, but for those of you who are not, ABEC is currently celebrating over 50 years of engineering and manufacturing custom biopharmaceutical production equipment. This includes bioreactors, fermenters, and supporting upstream and downstream equipment and piping. We supply our customers with customized solutions in stainless steel, single use, or a hybrid of the two technologies. So the focus of my presentation today will be on how ABEC uses MSTAR CFD to support our work. I'll walk through a case study to illustrate my points. On the right of the slide, I've listed some of the most common characteristics our customers want to evaluate with CFD. The case study will involve the first three, so blend time, mass transfer, and shear stress. I will also share some thoughts on how to best interpret results from a CFD study, including some things to be wary of if you look at other CFD results in the future. So first, let's establish what CFD is good at. CFD is extremely useful when it comes to visualizing what is going on inside a vessel, especially when it isn't practical to observe it in real life. In many cases, CFD can be significantly more cost-effective than performing live experiments. Often, simulations can be done in parallel to experiments or production runs, which can help avoid equipment downtime. So speaking specifically to ABEC's interests, CFD helps us confirm whether design changes we've made have the desired results before we build the equipment, which can save us and our customers significant time and effort. However, there are limitations. So first and foremost, simulations take time, right? So more complex simulations take more time. This means that using CFD to search for answers can quickly eat up time and resources. So you'll want to know exactly which results you're seeking when you decide to use CFD as a tool. The other thing to note here is that simulations are heavily dependent on what information you put in. Because so many different physical phenomena are modeled, something as simple as rounding a decimal will affect your accuracy. Accuracy is a bit of a loaded term for CFD. Everybody wants better accuracy. It's certainly possible to reach high levels of accuracy with enough time and supporting data. You heard John mention the term digital twin for this sort of high fidelity model. MSTAR CFD is more than capable of producing digital twins. The unfortunate reality, though, is that in order to build something approaching digital twin levels of simulation, you will need to have a library of experimental results specifically for that system to calibrate the model. This calibration is required to overcome some of CFD's inherent sources of inaccuracy. So, for example, the CFD software has some mathematical assumptions baked into it that limit how accurate you can get out of the box. I'll speak to some more of those assumptions shortly. Additionally, you might need simulations to run more quickly to meet project deadlines. So to speed things up, you might choose to make simplifications, such as using a coarser lattice or disabling physics that aren't of immediate interest to you. In this graph here, you can see an example of the consequences of simplification. So notice how the impeller power number drifts away from its true value as we reduce the lattice density. Every CFD simulation is full of balancing acts between accuracy and speed. Every decision you make is going to be a trade-off. One of the things I hope to show you today is that you can still get meaningful results even without digital twin levels of fidelity. So through experience, we found that CFD works very well when making comparisons. The amount of information available to us varies by customer, but frequently we're missing information. So rather than performing lengthy or costly experiments to try to find the missing information, we simplify the model in ways that don't compromise the results that we want. So by focusing on specific objectives, we can place more emphasis on the direction and magnitude of change in the results. The direction of change tells us if we've improved or declined in performance, and the magnitude of change gives us a sense of how effective the change was. So for example, did we double the value, triple the value, and so on. In this way, we find the sweet spot, which is a model that is good enough to observe the things that we care about. Because we aren't necessarily expecting to determine exact values in the results, at least with the initial model, We don't need to be as picky about what sorts of assumptions are being made as long as they were logical assumptions. However, this does mean that we need to be very careful to keep operating conditions consistent between simulations so that the comparison is meaningful. So the case study I'd like to present today was brought to us by a customer seeking to scale their production capacity. The customer had been operating at 200 liters, but in attempting to scale up to 2,000 liters, they found that a single-use bioreactor from another vendor was unable to meet the mass transfer requirements of their process. So we were asked to perform a textbook study to take their process from 200 to 2,000 liters and to perform a CFD comparison between ABEC's proposed design and their existing 2,000 liter design. So for the purposes of this presentation, I'll refer to the ABEC system as a CSR, which stands for custom single run, and to the other vendor system as a sub. Many of you are probably familiar with what goes into a textbook study, but I'll summarize it briefly here. So essentially, we establish a handful of properties for the reactors and attempt to maintain those properties at different volumes. So for example, the most basic feature to keep consistent is aspect ratio, which is the relationship between liquid height and vessel diameter. In this case, the customer was specifically looking to maximize impeller power per volume. So this is the measure of impeller effectiveness that factors in things like impeller type, impeller quantity, and impeller spacing. We need to limit the impeller tip speed for shear sensitivity reasons, and we also needed to limit the sparge gas entrance velocity, likewise for shear reasons. So we use the textbook study to decide the physical configuration and operating conditions that will meet the performance requirements. In this scenario, the textbook study determined the impeller type, impeller RPM, and sparging flow rates with the intent to improve overall mass transfer. So after calculating the expected performance using the textbook study, we then model the existing sub and our proposed CSR in MSTAR CFD. And if we've done our job properly, the results of the textbook study and simulation should match. Here are a few of equations that play a role both in the textbook and the CFD analysis. So for example, here we have the relationship between impeller power number and power number. This is used to determine power per volume, which has knock-on effects for just about everything that we're going to simulate. We also have the initial bubble size, which plays a part in both the sparger design and its representation in CFD. We have the equilibrium bubble diameter, which plays a large role in mass transfer simulation, as it controls the local bubble diameters and thus your bubble surface area. And finally, we have the mass transfer coefficient, or KLA. There are a variety of different expressions in literature for this, but we'll be using the KL and A expressions shown here. A longer description for how the equilibrium bubble diameter and KLA interacts in MSTAR CFD can be found on MSTAR's documentation site. Now, digging a little further into the CFD, there are a few things to keep in mind for model setup. As John has mentioned earlier, MSTAR is a GPU-based solver. So this means that with more powerful GPUs, you can run more complex models. One of the most fundamental things that affects complexity is the lattice size. So the lattice defines points in space where the CFD performs the Navier-Stokes calculations. It also determines the fidelity of solid objects in the model. So for example, here on the left, you can see a visualization of the lattice. You can also see that at this lattice density, the smooth curved surface of the vessel bottom head is represented as distinct voxels. You may also recall the graph that I showed earlier about the impeller power number at different lattice densities. That graph shows what is known as a sensitivity study. So before we do an official simulation, we often perform multiple test runs at different lattice densities to ensure that the model is sufficient to meet our needs. You can always brute force your simulations by making the lattice extremely dense, but then your runtimes can very quickly extend from days into weeks, even taking advantage of MSTAR's GPU-based solver. So the sensitivity study essentially helps us find a lattice density that is accurate enough without bloating the runtime. Another thing that we need to determine is the simulation time step. If the time step is too large, then the simulation has a hard time keeping track of where fluid moves at any given moment. If it's too small, even simple flow simulations can take forever. You also need to consider how you want to view your results. So this choice between 2D and 3D can mean the difference between a few gigabytes of data and several terabytes of data at the end of your simulation. Lastly, the user needs to establish the rheology or fluid properties. Now, for this case study, we're dealing with a partially filled tank. At this size, we aren't that concerned with surface aeration effects, so we'll use a free surface fluid model. And we don't know the exact properties of the fluid, but will use the properties of water at the given temperature with some adjustments to make it behave more like a broth. The fluid rheology and process temperatures are going to be consistent between the two simulations, but the physical characteristics and operating parameters are not. So on the left, I've listed the process conditions set by our customer for the sub. On the right, I've got the conditions that were decided in the textbook study for the CSR. You'll note that the CSR's agitation RPM was set according to the impeller tip speed limit imposed by the customer. Now, remember that in this study, we were meant to maximize the power per volume. So you'll note that the values for RPM and power per volume in each of these systems is quite different. And because the working volume is 2,000 liters in both cases, the difference in power per volume immediately tells us that the capabilities of these two systems will be quite different under the constraints given by our customer. In terms of gassing, we can see that the values are slightly different between the two, and that the flow rates of air and oxygen are flipped. However, since we're looking at the KLA in this scenario and not the oxygen transfer rate or oxygen uptake rate, we are more concerned about total gas volume than specific gas mixture at this stage. Before we get into the simulation results, I want to establish some caveats. So first, we have attempted to maintain as much similarity between the systems as possible in order for our comparison to hold. By this, I mean that the general parameters like lattice spacing and fluid rheology have been kept consistent. However, as I pointed out, there are physical differences between the two systems. Performance is expected to be quite different between the two. Additionally, be aware that the visualizations represented here are a selection of the data. They show a moment in time and do not necessarily form a complete picture. When you look at any CFD results, they often show a parameter with a user-defined range to highlight some characteristic. So be aware that some similar looking pictures may actually show wildly different ranges of values. And finally, on the right, I've listed some of the results that we'll be considering today. These models were set up to provide these specific results. If you're interested in anything not listed here, you'd likely need a different model to see those. So here I've got some screenshots of the vessels that we modeled. So a couple things to note. The sub on the left, you'll see it has a single small angle-mounted impeller. It has a ring of sintered disc sparges below the impeller, as well as a T-sparge that we assume to be in the bottom center of the vessel. On the right, the ABEC CSR has two center-mounted low-shear impellers with two separate joule hole sparges just below them. In both models, there's a small magenta dot that represents a probe located at the vessel probe belt, and we'll use this probe to mimic how measurements might be taken in a live experiment. In these pictures, I've also highlighted a red cube near the top front of the vessel. These cubes mark the location where liquid additions are going to come into the vessel. So this is where we'll add liquid scalar that's used to evaluate blending performance. So now let's look at some of the results. So first up here, we have the flow fields. So these two images show fluid velocity magnitude in 2D planes in the sub, in the CSR, with lines to indicate flow. So we have front and side views of each, so you can get a sense of the flow direction. I've also set up the color gradients so that the ranges are equal for both images. So looking at the picture on the left, we can see that the sub has a region with high fluid velocity at the impeller and vessel bottom head, but much less velocity everywhere else. We also have a slight dip in the free surface and a zone in the center of the vessel that looks like it's forming a vortex. On the right, we can see that the CSR has a significantly different flow pattern. So this impeller arrangement creates turbulence in the upper regions and has higher fluid velocities basically everywhere in the vessel. If we look at the impeller power number results reported by the CFD, we can see that the flow field results make sense. Right? The combination of the two impellers and baffles combined to give the CSR approximately 3 times the impeller number of the sub. If we look at the blend times, the results become even more pronounced. So when we're performing these sorts of studies, we allow the mixer some time to warm up so that the flow fields are established. And then we add the scalar and we wait. So in this case, on this graph, time 0 represents the moment that we've added the scalar. So we have 2 methods that we usually use to determine blend time. The first method, shown on this graph, uses the relative standard deviation, or RSD, of scalar volume fraction. So this is a way to gauge essentially how scalar concentration differs at all of the lattice points that contain fluid inside the vessel. So using the RSD method, the system is considered 95% blended when the RSD drops below 5%. So you see here on the graphs that the sub, This blend time occurs at 111 seconds after the scalar is added. And for the CSR, this occurs at 27.6 seconds after addition, so roughly 1/4 of the time. If we look again at the flow fields, this makes sense. So remember that the scalar is going to be added near the surface. The sub has smooth cyclical fluid motion at the top head and not much turbulence to distribute the scalar upwards and downwards. It takes a long time for the scalar to finally reach the impeller, and then the impeller has a hard time moving that fluid back up into the upper region. If we look at the CSR, we can see that the top of the vessel has turbulent flow, and then you can also see that the dark red zones between the impellers. This shows good axial flow transition, which moves the fluid vertically and results in faster mixing overall. The second method we use mimics an experimental test by looking at probe feedback. So we first calculate the expected final volume fraction based on how much scalar was added and the known volume of fluid. We then find the instant when the scalar is within plus or minus 5% of that final value to determine a blend time. So unlike the RSD method I showed earlier, right, this graph has spikes where volumes of high scalar concentration wash past the probe, as would happen in a live experiment. And looking at the graph here, you can see the results are similar to those using the RSD method. And in both cases, right, the CSR blend time is significantly shorter than that of the sub. So next, we'll look at some of the mass transfer results. KLA results in particular are heavily dependent on user inputs for the liquid and gas properties. MSTAR has a whole host of model setup options that need to be considered. So for example, MSTAR models the bubbles as Lagrangian particles or spheres up to around 1 centimeter in diameter by default. If the bubbles are expected to exceed that diameter, right, the model has to be set up differently. Likewise, if the system is expected to have a very large quantity of bubbles or bubbles with a long residence time, you may need to use the parcel method to make it manageable. Surface tension is obviously critical for bubble behavior, but so is the energy dissipation rate, or EDR. EDR is a major factor in just about every aspect of bubble behavior, including equilibrium bubble size, bubble breakup, and coalescence. So EDR is a local physical property calculated by the simulation. And like much of what I'm showing today, it relates back to the impeller power number that we discussed earlier. So recall that the CSR has much larger impeller power number and power per volume at these operating conditions. So looking at the EDR results for the two systems, we can see that the mean EDR of the CSR is about double that of the sub at steady state. So this means that generally the fluid in the CSR has higher energy. And if you recall the flow fields shown earlier, this makes sense. Higher average energy in the fluid benefits us in two ways. Right? So firstly, higher energy allows us to overcome surface tension. In the bottom left of the screen, I've included the formula for equilibrium bubble diameter that I mentioned earlier. So you see that the surface tension and fluid density are constants in the simulation, which means that the EDR in the denominator is the determining factor in bubble size. So a system with more energy will experience more bubble breakup events and have smaller bubbles overall. This graph here shows the mean diameter of every bubble in the system at a given time. And you can see that the CSR average is about 80% of the sub average at steady state. The smaller bubbles in the CSR equate to more bubble surface area, which again contributes to our ultimate goal of improved mass transfer. Secondly, the elevated EDR helps bring us closer to homogeneous conditions. So larger EDR results in smaller bubbles, and smaller bubbles are carried more effectively by the fluid flow. So these two images here show the individual bubbles in the system colored by diameter. So if you look at the sub on the left, you can see that once the bubbles leave the high energy zone immediately surrounding the impeller, they begin to rise directly to the surface and they don't really migrate to the far side of the vessel. However, in the CSR on the right, you can see that the higher and more even energy distribution keeps the bubbles smaller and disperses them more effectively. So finally, let's look at the actual KLA results. At our steady state condition, we can see that the KLA in the CSR is about 3 times that of the sub under these conditions. This aligns with our understanding that the CSR has a higher and more even distribution of energy, which contributes to a larger quantity of more evenly distributed smaller bubbles. So this in turn means a larger surface area through which mass transfer can occur. Here, I'll reiterate that because these models were not calibrated against experimental results, the numbers shown here are not immediately useful for making statements about the real-world performance. They are, however, useful to illustrate our point about magnitude and direction of change. So we would expect the actual KLA values in the CSR after calibration to be about 3 times that of the sub, should we perform the study as a live experiment. So far, the ABEC CSR looks pretty good. We have shorter blend times and we have higher KLA. But here's where that higher energy level might come back to bite us. So we look at shear stress. Shear is a major concern in many bioprocess applications. However, it's rare for our customers to provide a hard and fast number that for their cells. So generally that means that our customers just want less shear, but they can't usually articulate how much shear is too much. Also, since our liquid is often modeled as water-like with an assumed viscosity, the results for shear stress will likely be less than in the live process. So therefore, in our simulation, we are less concerned with the exact values in the CFD, but we're more concerned about relative averages and maximums. Now, because this is at heart a mathematical model, there is the propensity for extreme values to become more extreme over time. So this can make absolute maximums unreliable. So in this case, we'll take a statistical approach to try to rationalize all of these results. So in this table on the right, we have the shear stress average, maximum, and minimum values, as well as quantiles for 95, 99, and 99.9%. For anyone less statistically inclined, the value shown for the 95% quantile means that 95% of all lattice points experience a shear stress value less than that. So we see here in our comparison that the sub has an average shear slightly more than half of the CSR. So sub has 0.009 versus the CSR's 0.017, meaning that most of the fluid in the sub experiences significantly less shear. However, if we look at the 99.9% quantile in absolute maximums, we see that the sub values exceed that of the CSR. So again, this information tracks with our understanding that the sub volume is mostly low energy and has an extremely high energy zone at the impeller. I have the same shear stress results now shown as normalized histograms. So for these graphs, the y-axis shows the likelihood of any particular lattice point to have the shear stress value shown on the x-axis. You can see that the sub results in orange are heavily skewed. A large portion of the lattice points experience very, very little shear. But with the two histograms overlaid, you can see that the CSR has a more even distribution of shear stress values, as well as a slightly higher value on average. It isn't really possible to examine the upper range at this scale, so we'll look at the graphs separately next. So while it's still difficult to see the high ends on the graphs at this scale, we now have the quantiles displayed. So you'll note that the larger gap between the 99 and 99.9% quantiles for the sub, this means that it has a small zone, about 1% of the fluid volume, that experiences more intense shear than the CSR. So it's likely that the top 0.1% experiences much higher shear as well. So comparing the two 99.9% values, we would expect the absolute maximum shear in the CSR to be less than the sub. Again, how much less? We can't necessarily rely on exact numbers using these particular models, but the absolute maximums reported by the solver indicate that the CSR maximum could be as much as about 30% less than the subs. Here we have a visualization of these shear zones. So these two images use the same color scale with 0 pascals as transparent and 0.2 pascals as dark red. On the left, we can see that the majority of the sub is essentially transparent or a very faint blue with an elevated shear region surrounding the impeller. On the right, we can see that most of the CSR is a light blue with some sort of middle green and yellows at one of the baffles and at the impeller tips. The darkest reds are only really visible in the wake of these subs impeller blades. So the takeaway for all these shear stress results, if shear stress is a major concern for the process, it would be important to know the critical limits, which will immediately determine whether these impeller configurations in both systems are viable for you. If you don't know the critical limits, you'll have to make a more subjective decision. If the subs can handle some shear, you might decide that CSR is likely a better option. It has slightly lower statistical maximums for shear and significantly better blending and KLA performance. On the flip side, you might look at this and say, my cells can't handle the consistent elevated shear, in which case I would prefer the sub, which has a smaller zone of higher shear, which minimizes the time that my cells are exposed to it. Each conclusion is valid, but each user has to consider their cell's limits to decide what is critical to them and which design best fits their needs. So to wrap up, I guess hopefully I've demonstrated to you the usefulness of CFD as an effective way to evaluate specific aspects of vessel design. I'd like to reiterate one final time that with CFD, you get out as much as you put in. So if you're willing to invest the time and resources into developing digital twin levels of models, you can create them in ways that mimic live conditions. However, I suggest that you use your judgment about two things. Firstly, do you have enough information to develop a high fidelity model? And secondly, do you actually need a high fidelity model to find the answers you're looking for? At ABEC, we found that if you focus on specific results, your goals can be achieved with relatively simple models and limited information. For designing biopharma vessels, CFD is an effective and efficient tool to test performance before and after a change. This is especially useful for quantifying and visualizing phenomena like blend time or shear stress that can be difficult to capture in a live experiment. Finally, all of this can be done with models that are just as sophisticated as they need to be in order to reach useful conclusions. So at this point, I'd like to thank you all for your time and attention. I also like to thank John, Amber, and the MSTAR team for the incredible support they've provided me over the past few years as I've learned more about CFD. And at this time, I'll hand you back over to Amber.
Okay, wow. Daniel, that was so great. It was just fascinating to hear about MSTAR from a user perspective and the impact it can have on vessel design and ultimately industrial production. And that was fabulous. And John, as usual, great summary of MSTAR. So this is the time we open it up to you, our audience. If you have any questions, please pop those in the chat, and we'd love to fill up our last few minutes here with some answers to your questions and feedback. All right, here we go. First question. Thanks for the presentation. I was just wondering if John might explain a bit more on the breakup collision kernels. Any specific kernels implemented or validated?
Sure thing. Let me go ahead and call up some documentation here that speaks to this, and then I'll share my screen. Okay, and peer review validation trajectory. Okay. Okay, yeah, let me go share here. Can folks see my screen now? Is this going through? We good?
Looks great.
Okay, perfect. Let me go ahead and speak to this point. Also, one other just side point that I thought was really interesting, motion before I speak to that. Daniel, you made this passing comment about simulations may not, and it was correct, simulations may not be reproducible. And that might have sounded counterintuitive to some people that said, well, is it just deterministic calculation? No. When you're running like a time accurate LES simulation, whether it be an MSTARs, GPUs, or CPUs, you do get different results between runs. And this has been spoken about in the literature. Sorry, the piqued my interest, I want to speak to the point. So this has been talked about. Whether it be GPU codes like MSTAR or CPU codes like, in this case, I think they used ANSYS. But so people can run, 50 different experiments to predict blend time and get a distribution of blend times, which makes sense. It depends how the universe felt that way. You could run 50 different experiments of MSTAR and get some variation. And you can run 50 different simulations of LAS simulation in a finite volume-based tool and get some variation. So this idea that like, well, if I turn on my computer and start the simulation, I'll get the same result every day. No, just as when you turn on your reactor and add a salt bolus, you're not getting the same blend time every time. And so, yeah, there is inherent irreducibility reproducibility inside simulations. And what's neat about this was actually kind of mysterious that is really confusing is that the variation is consistent with the experimental variation, which is kind of strange because why would the universe reproduce a similar variation in GPU as it did in an actual physical plant? And so that's a point of actual like philosophical consideration about why that happens. But either way, I digress. Let's speak briefly about these breakup models. In general, as discussed, we're modeling breakup and coalescence at the level of the individual bubble. Okay, so we're tracking one bubble, how it's moving through the system to understand what sort of energy dissipation landscape it's experiencing, or what sort of strain accumulation it's experiencing in a way that eventually causes breakup. One model that we developed was based on local energy dissipation rate and a stretching time scale. We talk about this in the literature, paper shown here. I can send those to you directly if you want to see them. But this says that if a bubble sees an EDR above a critical value for above a certain stretching duration related to the second bending mode, second stretching mode, it'll undergo a breakup event with the size of the two daughter fragments calculated from, again, breakup theory. Likewise, coalescence, we look at two bubbles coming together, and if they have a critical Reynolds number, they coalesce. If not, they bounce. And so this has been spoken about a lot in some of our own publications. There are other approaches as well, which are in MSTAR and spoken of in the literature. Like here was a neat paper written by some of our colleagues at TU Hamburg, where they did not use our EDR-based approach. They instead used a trajectory-based model, which mimicked the bubble as something like an object that would stretch and deform and accumulate that stretch and deform. Think of like a spring dashpot type model, okay? And it's just a different type of approach to modeling bubble breakup. And it actually worked very, very well when they compared their measured to predicted bubble size distributions. And so there are a couple ways to attack this. This paper is actually really neat, and it's something I've been using more in my modeling because we have both options at MSTAR. But again, the similarities are that they both appeal to individual bubbles breaking up at the level of the individual bubble. One of the earlier ones in MSTAR appealed to EDR. This appeals to both spring and dashpot theory. This one's stronger because it has immediate comparison to snapshots and measured bubble size distribution. The other one compares very well against KLA. And so, yeah, there are a couple of different approaches. They both do validate well, but importantly, real importantly, they both appeal to breakup at the level of the bubble, which makes them agnostic to scale. If it works in 5 liters, we would expect it to work at 50,000 liters, okay? Because the bubbles don't stop, look around, and see how big the bubble is before they break up. All they know and care about is what they've been experiencing either immediately or in the past few bubble diameters of motion when deciding whether or not to break up into fragments. But yeah, literature abounds. We can speak more about that offline should folks have deeper questions.
Okay, yeah, we also had there was a request for a link to the paper about reproducibility that you mentioned, John.
Yeah,
Looks like Johannes shared another one, but if you wouldn't mind sharing that one in the chat, that would be great.
Yeah, there are a couple of those.
Okay, second question, is it possible to combine the CFD simulation with the kinetic model of the cells and simulate a bioprocess and not only the hydrodynamics characterization to inform bioprocess design?
Oh, buddy, you got to check into some of these webinars. Yeah, 100% yes. In fact, this is what we've done with Pfizer. We just published this earlier this year. I'll share the paper right now. Yes, we can look at how we can integrate cell growth dynamics into CFD simulations. Here, my screen's still sharing. I think this headline and title matches your question. Integrative in silico models from mammalian cell cultures and sequence bioreactors, bridging hydrodynamics, kinetics, process control. Yeah, we got this. Okay, so in this paper with Pfizer, we talk about this exact problem, how we can use, again, CFD, PID controllers. You can see where that image came from. You're kind of watching the sausage get made here. And then like actual growth models. These are monad-based models. They can be whatever you want them to be. For predicting how cell density changes over time and how lactate, cell density, the metabolites, et cetera, change over time, and how modifying nutrient feeding schedules, PID controllers, et cetera, can ultimately optimize cell density and titer production. So yeah, this is one of our most interesting areas of research. In fact, if you looked at my screen right now, like the model I'm running like right now is this thing, cell death, et cetera, all going on in tandem and wired up with PIDs to inform optimal growth. So yeah, we do that very well. That's kind of our bread and butter right now.
Yeah. Yes. Again, right. To my point, I guess I'll say that all of those things are going to be sort of mathematically driven within MSTAR. So again, like while all of it is possible, the amount of information that you'll have to have from experimental testing and the like becomes infinitely larger the more complex you want to of a process that you want to model. So you can sort of approach it sort of stepwise if you've got the time for it. So keep that in mind.
I'm afraid it looks like we've hit our time here, our time limit. There's one more question. There's a couple more questions, but maybe we can address those after the webinar. We can get back to you with answers.
Yeah.
But want to thank John and Daniel for your wonderful presentations today, and remind everyone this webinar has been recorded, and you'll be able to access it on our website or through the documentation or on our YouTube page. And it's been great having you, Daniel. John, if you have any final words.
No, thank you so much, guys. Appreciate you.
No, thank you all for attending.
All right. Have a great day, everyone.
Thank you.